Hello, friends. Welcome back. Or if this is the first time you found your way here, welcome. I'm so glad you're here tonight. Close your eyes for just a moment. Try to imagine nothing. Not darkness, not silence, not even empty space. Nothing. No floor beneath you, no sky above, no breath, no time. Nothing at all. Did you feel it? That strange slipping where the mind reaches for an edge and finds none? That is the place where tonight's story begins. Before the first light, before the first atom, before the first heartbeat of time. What was there, and how did everything, every star, every ocean, every quiet breath you're taking right now, emerge from that impossible nothing? That is the question that has haunted physicists, philosophers, and dreamers for centuries. And tonight, we are going to drift into the very beginning of everything, slowly, gently, together. Before we begin this quiet journey, if you find comfort in these soft explorations of science and wonder, you might like to stay a while. You can gently tap the like button, subscribe, if you'd like more stories told softly into the night, and ring the little bell, not for noise, but so the next quiet evening can always find you again. Now, let's drift. Tonight we begin at the very threshold of existence, a place physicists call the Planck-scale, the smallest sliver of time and space that our mathematics can even describe. A boundary so extreme, so wild, so beyond ordinary imagination that even our best equations dissolve into silence there. And from that silence, everything you have ever known was born. Let me tell you something that most people get wrong about the Big Bang. When most of us hear the words Big Bang, we picture a massive explosion, a brilliant flash somewhere out in the darkness of space, like a firework going off at a single point and then expanding outward into a void. But that image, as beautiful as it feels, is deeply fundamentally mistaken. The Big Bang was not an explosion in space. It was the explosion of space itself. There was no out there into which the universe expanded. There was no empty stage waiting to be filled. Space-time, energy, matter, all of it came into being together in the same instant from the same impossible point. And that instant, that very first heartbeat, is what we call the Planck epoch. The Planck epoch lasted from the moment of creation, what physicists label at t equals 0 to approximately 10 to the power of negative 43 seconds. 10 to the negative 43. That is not a long time. In fact, it is so short that it makes even the blink of an eye feel like an eternity by comparison. And yet, in that incomprehensibly tiny sliver of time, the entire fate of the universe was being decided. The laws of physics themselves were still being written. Now here is something remarkable to sit with. We know a great deal about the universe. We understand stars, galaxies, black holes, quantum fields. Our science has reached extraordinary depths. And yet, when we try to look back to this very first moment, this Planck epoch, our equations break down completely. They return answers like infinity and undefined, which in mathematics is a polite way of saying we have no idea what is happening here. It is as though the universe has drawn a veil over its own birth, a wall of mathematical silence beyond which our instruments cannot see. Physicists call this the Planck wall. And tonight, we are going to approach that wall carefully, quietly, and peer as close as any human mind has ever dared to look. But first, before we reach the wall, let us stand here for a moment in the ordinary dark and feel the weight of the question. Consider this. You are made of atoms. Every atom in your body, the carbon in your cells, the iron in your blood, the oxygen carried gently through your lungs. With each breath, every single one of them can trace its lineage back to the first 3 minutes of the universe's life. And the energy that holds those atoms together, that makes the electrons dance around their nuclei in precise quantum orbits, that energy has been flowing unbroken since the very first moment of creation. You are not separate from the Big Bang. You are part of its story still unfolding. That idea, quiet and vast, is one I'd like you to hold gently through everything we explore tonight. Now let us talk about the state of things, not just in science, but in history. Human beings have always looked up at the sky and asked, where did all of this come from? The ancient Egyptians believed the universe emerged from the primordial waters of Nun, a dark, formless ocean, when the first hill of dry land rose from the deep. Creation is emergence from chaos into form. It is a surprisingly resonant metaphor when you consider how modern cosmology describes the quantum vacuum of the early universe. The ancient Greeks imagined the cosmos as eternal, always existing, always cycling. Aristotle himself argued that the universe had no beginning, because to have a beginning, something had to cause it, and that cause itself would need a beginning, and so on, forever. An infinite regress. He concluded the universe was simply eternal, and for centuries that was the comfortable assumption in Western science as well. It took until 1927 for a quiet Belgian priest and physicist named Georges Lemaitre to first propose mathematically that the universe was expanding. And if it was expanding now, then running the clock backward, everything must once have been gathered into a single, unimaginably dense point. He called it the primeval atom, the cosmic egg, from which all of space and time hatched. Most scientists, including Einstein himself, resisted the idea. Einstein famously modified his own equations with what he called the cosmological constant, essentially a mathematical patch specifically to make the universe appear static and eternal, because the idea of a universe with a beginning made him deeply uncomfortable. He later called it the greatest blunder of his career. The confirmation came in 1929 when Edwin Hubble, working at the Mount Wilson Observatory in California on dark, clear desert nights, measured the light from distant galaxies and found something extraordinary. The galaxies were moving away from us, all of them, in every direction. The further away a galaxy was, the faster it was retreating. The universe was not static, it was expanding, and the implications were unavoidable. Lemaitre had been right. There was a beginning. That beginning is what we now call the Big Bang, a name. Ironically, that was coined in 1949 by the British astronomer Fred Hoyle, who was actually trying to mock the theory. He used the phrase Big Bang dismissively in a radio broadcast to describe what he considered a ridiculous idea. The name stuck, and the theory he mocked became one of the most well-supported and experimentally confirmed frameworks in the history of science. That is perhaps a small and gentle lesson hidden inside the cosmos itself. Sometimes the things we dismiss, the ideas that seem too strange, too vast, too inconvenient, are the ones that turn out to be true. Let's pause here for a moment and ask, and this is something I truly love to think about, if the universe has a beginning. What does that mean for the concept of before? When we say the Big Bang happened 8 billion years ago, we naturally want to ask what came before that. But here's the thing, time itself. As far as we understand, it did not exist before the Big Bang. Time is not a container that the universe was poured into. Time is a property of the universe. It emerged alongside space matter and energy. Asking what happened before the Big Bang is, according to our current understanding, a little like asking what is north of the North Pole. There is no before, not because something is hiding there, but because the very concept of before requires time to exist first, and time began here. The physicist Stephen Hawking liked to describe it this way, imagining the South Pole on the surface of the Earth, and then asking, what is south of the South Pole? The question feels meaningful, but there is simply nowhere to go. You have reached the edge of the surface itself. The beginning of time is like that edge. And yet, and this is where things become wonderfully strange and wonderfully alive, not everyone agrees that this is the full picture. Some physicists and cosmologists believe that our Big Bang was not truly the beginning of everything, that it may have been a transition, a bouncing point, a moment, where a previous universe collapsed under its own gravity and then rebounded, exploding outward in what we experience as our creation. This idea, called the cyclic or bouncing universe model, suggests that time and existence may be far older than we can measure an eternal sequence of collapses and rebirths, each universe seeding the next. Others believe our universe is one bubble in an infinite sea of bubbles, a vast, ever-expanding multiverse, in which big bangs are constantly happening, each one giving birth to a universe with slightly different laws of physics, different constants, different possibilities, and still others following the work of Stephen Hawking and James Hartley, propose that the universe has no boundary at all in time, that asking for a beginning is mathematically ill-formed, and that what we call the Big Bang is simply one pole of a four-dimensional sphere, not a beginning, but a geometry. These ideas are not science fiction. They are serious, mathematically rigorous proposals being debated right now in universities and observatories, and late-night conversations between people who have spent their lives trying to understand the deepest nature of reality. And none of them have been proven. We are still in so many ways children standing at the edge of a great ocean, listening to the waves, watching the horizon, wondering what is beyond. There is something humbling and beautiful about that. The universe began, or transitioned, or bounced, or simply is in a state that no instrument we currently possess can directly observe. Everything we know about the Big Bang comes from traces, echoes, the faint glow of ancient light, the ratios of hydrogen and helium in the oldest stars, the subtle ripples in the temperature of the cosmic microwave background, that whisper of radiation that fills all of space, even now, even tonight, as you rest a remnant of the universe's infancy still washing gently through you. You are even now bathed in the afterglow of creation, softly, constantly, without end. Hold that thought. Let it settle somewhere quiet inside you, because from here, from this gentle edge between knowing and wondering, we are going to go deeper, much deeper, into the question of what was there before t=0, into the strange and shimmering world of quantum gravity, into the moment when the laws of physics themselves were not yet decided, into the Planck wall and what our most daring theories imagine might lie beyond it. The further back we reach the stranger, and more beautiful the story becomes. And it all begins right here, right now, in the dark, in the quiet, in the wondering, just like you tonight. What if the universe you were living in right now, every galaxy, every star, every quiet breath, every dream was not the first? What if before our Big Bang there was another universe, and before that, another, and before that? An endless chain of worlds collapsing and rebirthing, stretching back through a time so deep it has no floor. That question, what came before t=0, is one of the most contested, most quietly radical questions in all of modern science. And tonight we are going to sit inside it for a while. Now, as we explored in the opening of our journey, time itself is thought to have begun with the Big Bang. But here is the thing that makes certain physicists lose sleep in the most fascinating way possible. Our equations do not actually forbid a before. They simply break down before they can answer it. And that is a very different thing. A broken calculator does not mean the answer doesn't exist. It may simply mean we are using the wrong tool. So, tonight in this quiet hour, let us look at three of the most serious, most beautifully strange proposals that physicists have offered in answer to that oldest of questions. Three different visions of what, if anything, lay before the silence. The first is perhaps the most poetic. It is called the Hartle-Hawking no-boundary proposal, and it was developed in 1983 by two physicists, James Hartle at the University of California, Santa Barbara, and Stephen Hawking at Cambridge. Their idea was both mathematically sophisticated and philosophically breathtaking. They proposed that the universe has no boundary in time, that asking for a moment before the Big Bang is in a deep sense a category error. To understand this, imagine the surface of the Earth. As you move southward, you approach the South Pole. And at the South Pole, the concept of south dissolves. There is nowhere further south to go. But the Earth does not end there. The surface simply curves back on itself. The pole is not an edge. It is just a point where a particular direction runs out. Hawking suggested that time near the Big Bang behaves in a similar way. It curves and smooths into a fourth spatial dimension, so that the beginning is not a hard edge or a wall, but a gentle rounding off like the tip of a rugby ball. In this picture, There is no before. Not because something is hiding there, but because the geometry of space-time itself simply has no boundary to cross. There was no first moment. Time tapers to a point, and the point is smooth. The universe in this view is self-contained. It asks for no cause. It requires no creator. It simply is. Hawking himself said that if this proposal were correct, it would mean the universe was completely self-contained and not affected by anything outside itself. It would simply be. What place, then, for a creator? That one sentence caused quite a stir when his book, A Brief History of Time, was published in 1988, a book that spent an extraordinary 237 weeks on the British Sunday Times bestseller list, which remains a record for a science book. The public hunger for this question, where did everything come from, was enormous. It still is. But the Hartley-Hawking proposal, elegant as it is not the only serious answer. The second vision is older in spirit, though newer in its scientific form. It is the idea of the cyclic universe, sometimes called the ekpyrotic model, from the ancient Greek word ekpyrosis, meaning conflagration, or world on fire. In its modern form, this model was developed in the early 2000s by physicists Paul Steinhardt at Princeton and Neil Turok at Cambridge, and it draws strikingly from string theory. The core idea is this: our universe exists on a thin three-dimensional membrane floating in a higher dimensional space, what physicists call a brane. And there is another such membrane nearby, parallel to ours and visible to us, separated not by ordinary distance, but by an extra spatial dimension we cannot perceive. Very slowly, over trillions of years, these two branes drift toward each other through the hidden dimension. And then they collide. The collision releases an enormous burst of energy, filling our brain with heat and matter and motion. That collision is our Big Bang. And then the branes drift apart again. The universe expands. Stars are born and die. Galaxies spiral and fade. Black holes evaporate. Everything cools and dims. And then slowly, inexorably, the branes are drawn together again. Another collision, another Big Bang, another universe, cyclic, eternal, without beginning, without end. In this picture, our Big Bang was not a beginning at all. It was a transition, a moment of violent luminous contact between two great membranes in a darkness we cannot see. And the universe before ours, the one that ended in that collision, was not nothing. It was a vast, cold, nearly empty cosmos, stretching out in silence for trillions of years, slowly forgetting itself before the fire came again. That image, a universe quietly dying in the dark, not knowing it was about to be reborn, as something new, is one I find deeply moving. There is something in it that resonates perhaps with things closer to home, endings that are not endings, silence that precedes a new kind of sound. Now here is a common misconception worth pausing on. Many people, when they first hear about cyclic or eternal models of the universe, assume that they conflict with the Big Bang. They don't. The Big Bang, the hot, dense, rapidly expanding early universe, is not in question in these models. What changes is the interpretation of what the Big Bang was. Whether it was a true beginning, or a transition, or a collision, the expansion and cooling of the universe that followed is fully consistent with everything we observe. The evidence for the Big Bang itself, the cosmic microwave background, the abundance of light elements, the distribution of galaxies remains intact. It is only the question of origin that these models address differently. The data is not disputed, the meaning is, and that distinction matters. The third vision is the one that perhaps stretches the imagination furthest. It is called eternal inflation, and it was first proposed by physicist Alexander Vilenkin in 1983, and developed further by André Linde, who called his version chaotic inflation. We will talk more about inflation itself, the extraordinary rapid expansion of the early universe, in a later part of tonight's journey. But the key idea here for understanding what came before is this: in eternal inflation, our Big Bang was not a singular event. It was one bubble in an infinite sea of bubbles. Inflation, the rapid exponential expansion of space, did not simply happen once and then stop. It is, according to this model, still happening in a vast, roiling, inflationary multiverse that stretches endlessly in every direction, forever spawning new regions of space, where inflation locally slows, energy condenses, and a new universe explodes into being. Our Big Bang was one such moment of local condensation, one bubble, one island of relative calm in an infinite foaming ocean of inflation that has been going on and will go on forever. In this picture, there is no before our universe in the ordinary sense, because the inflationary background in which our bubble formed is itself eternal, with no beginning and no end. We emerge from it. But it was not created for us or because of us. We are in this vision one among an uncountable infinity of universes, each one born from the same endless, mindless, magnificent churning of quantum space. Now, I want to be honest with you here in the spirit of quiet honesty that I think late-night conversations deserve. None of these three models, the no-boundary proposal, the cyclic universe, or eternal inflation, has been confirmed by direct observation. Each of them makes predictions. Some of those predictions are being tested carefully and ingeniously by astronomers and physicists using instruments of extraordinary sensitivity. But as of now, we do not know which, if any, of these pictures is correct. We may not know for decades. We may in some ways never know, because the before of our universe may be causally disconnected from us in ways that make direct evidence forever inaccessible. And yet, and I think this is important to sit with the fact that we are asking these questions at all, and asking them rigorously and mathematically, is itself extraordinary. For most of human history, the question of what came before the universe was the exclusive territory of religion and philosophy. There was no scientific language in which to even frame it. Now there is. We have equations, we have predictions, we have observational tests, however imperfect. The border between knowable and unknowable is not fixed. It moves. It has always moved toward the strange, toward the deep, toward the questions we once thought no human mind could ever reach. Here is something to consider quietly as you rest. Every cosmological model we have discussed tonight shares one remarkable feature. In each of them, whether the universe is self-contained, cyclically reborn, or one bubble among infinite bubbles, the universe we live in is not special in the way we might instinctively feel it is. It is not the only one. It may not be the first. It may not be the last. And yet, here we are inside it, thinking, wondering, feeling the strange vertigo of trying to comprehend something so much larger than ourselves. That wondering, that very act of asking, may be one of the most remarkable things in the known universe. Research in cognitive science suggests that the human capacity for abstract curiosity, for asking questions that have no immediate survival value, for wondering about things that happened 13.8 billion years ago, is genuinely unusual. Perhaps unique among all the creatures we know of on this small blue world. We are the universe's way of asking about itself. Whatever came before the Big Bang, whether it was another universe and eternal inflation or nothing at all, it gave rise eventually to beings who would one day lie still in the dark and wonder. And that, I think, is worthy of a quiet kind of awe. But here is the deepest puzzle of all, the one that all three of these models still cannot fully escape. Even if the universe is cyclic, the cycles had to start somewhere. Even if the inflationary multiverse is eternal in the future, physicists like Arvin Board, Alan Guth, and Alexander Vilenkin proved in 2003 in what is now called the BGV theorem that any universe undergoing expansion must have had a beginning in the past. Even eternal inflation, they showed, cannot be truly past eternal. It must have had a starting point, a first moment, a boundary, and at that boundary, at the very first instant, we arrive again at the Planck wall, at the place where our equations dissolve, at the question that will not let go. What was there? What breathed fire into the equations and made a universe for them to describe? That question, first asked in those exact words by Stephen Hawking, has no scientific answer yet. It may be the last question standing long after every other mystery has been quietly solved. And it brings us now directly to the most extraordinary and least understood moment in all of cosmic history, the Planck epoch itself, the Wall of Fire, the place where temperature and density and energy reached values so extreme that our entire framework of physics simply ceases to function. The moment just ahead of us in this journey, where reality had no shape, no law, no certainty, only pure, seething, wild potential. Let's move closer. Imagine you are a cartographer. Your entire life, you have been drawing maps, precise, beautiful, reliable maps of every terrain on Earth. Mountains, coastlines, river deltas, desert plains. Every place you have ever sent your instruments, they have returned with clear, faithful data. And then one day you point them toward a single location, a specific coordinate, and every instrument you own goes silent. Not broken, not damaged, just silent. Returning nothing but the mathematical equivalent of a shrug. That location exists. You know it exists. You can calculate exactly where it is, but no tool you possess can tell you what is there. That is precisely the situation physicists find themselves in when they try to look back to the very first instant of the universe's life. The location in question is called the Planck epoch, and the silence of the instruments in this case, the silence of our equations, is called the Planck wall. We are now standing at the edge of the most extreme, most mysterious, most poorly understood moment in the history of everything. And before we try to peer beyond it, let us first understand exactly what it is and why it stops us. The Planck wall is not a physical barrier. It is an epistemological one, a boundary of knowledge. It marks the moment in cosmic history before which our two greatest theories of physics, quantum mechanics, and general relativity cease to function. And that in itself is one of the most fascinating facts in all of science. Let me explain why, because this is important and beautiful and worth slowing down for. Quantum mechanics is our theory of the very small. It describes with extraordinary precision the behavior of particles, atoms, photons, electrons, the fundamental forces that hold matter together. It is the most accurately tested theory in the history of science. Some of its predictions have been verified to an accuracy of 1 part in 10 billion, the equivalent of measuring the distance from New York to Los Angeles, and being wrong by less than the width of a human hair. It is by any measure a triumph of human thought. General relativity, on the other hand, is our theory of the very large. It describes gravity not as a force, but as the curvature of space-time itself, shaped by mass and energy. It predicted the bending of light around the sun, the existence of black holes, gravitational waves, the expansion of the universe. Every prediction it has ever made has been confirmed. It too is an extraordinary achievement. And here is the deep, quiet tragedy at the heart of modern physics. These two theories, each one almost impossibly accurate in its own domain, are fundamentally incompatible with each other. When physicists try to apply both simultaneously, as they must do when dealing with something that is both extremely small and extremely massive, like the early universe, the mathematics collapses. Terms become infinite. Answers become meaningless. The equations do not simply give wrong answers. They give no answers at all. The technical way to say this is that we lack a working theory of quantum gravity, a framework that could unify the quantum world and the gravitational world into a single coherent description. String theory is one candidate. Loop quantum gravity is another. There are others still, but none of them has been completed. None has been fully tested. And so, at the Planck scale, the regime where both quantum effects and gravitational effects are simultaneously enormous, we are for the moment blind. Now, what exactly is the Planck scale? It is defined by a set of natural units called Planck units derived in 1899 by the German physicist Max Planck himself, the same man whose work on black body radiation would launch the quantum revolution. Planck noticed something remarkable by combining the three most fundamental constants in physics: the speed of light, the gravitational constant, and the quantum of action. You could construct units of length time, mass, and temperature that were entirely natural, not defined by human conventions like meters or seconds, but defined by the deep structure of the universe itself. The Planck length is approximately 1.6 times 10 to the power of negative 35 meters. To give you a sense of how small that is, a proton is already about 10 to the negative 15 meters across. The Planck length is 20 orders of magnitude smaller than a proton. If an atom were scaled up to the size of the observable universe, the Planck length would be roughly the size of an atom. It is the smallest scale at which the concept of distance retains any meaning under our current physics. Below it, or more precisely in the regime where it governs space itself, may not be a smooth continuum. It may be something else entirely, something grainy, something discrete, something we do not yet have the language to describe. The Planck time is the time it takes light to travel one Planck length. That is approximately 5.4 times 10 to the negative 44 seconds. It is the smallest unit of time that our current physics can meaningfully speak about. Before one Planck time has elapsed after t equals 0, we cannot say what happened. Not because nothing happened, but because our framework for describing what happened has not yet been constructed. And the Planck temperature, the temperature of the universe at that first Planck instant, is approximately 1.4 times 10 to the 32nd power Kelvin, 142 nonillion degrees. That number is so large it is almost impossible to compare to anything familiar. The surface of the Sun is about 5,800 Kelvin. The core of a supernova reaches perhaps 100 billion Kelvin. The Planck temperature is approximately 100 million trillion times hotter than that. At this temperature, the thermal energy of particles is so extreme that gravity, normally the weakest of the four fundamental forces, by an enormous margin becomes as strong as the other three forces. All four forces are thought to be unified. At this scale, merge into a single undifferentiated superforce. We have no confirmed theory of what that superforce looks like. Its nature remains one of the deepest open questions in all of physics. Here is a common misconception worth pausing on, because it comes up often. People sometimes say that the Planck wall means physics breaks down at the Big Bang, as though the universe itself stopped following rules at that moment. But that is not quite right. What breaks down is not the universe. What breaks down is our description of it. The rules did not stop. Our ability to write them down did. That is a very important distinction. The universe at the Planck epoch was not lawless or chaotic in a colloquial sense. It was operating according to some deep unified framework that we have not yet discovered. The wall is in our minds, or more precisely in our mathematics, not in reality. This is in a strange way encouraging. It means there is something real to find. There is a theory waiting to be written, a language waiting to be invented. And some physicist, perhaps not yet born, perhaps already quietly working in a library somewhere, will one day find it. The history of physics is full of moments like this. Moments where the equations broke and the breaking turned out to be a door. In the late 1800s, physicists were deeply troubled by a puzzle in thermodynamics, the ultraviolet catastrophe, which predicted that hot objects should radiate infinite energy at high frequencies. The equations gave an absurd infinite answer, and from the attempt to fix that absurdity, Max Planck, the same Planck whose name graces all these scales, introduced the idea that energy came in discrete packets or quanta. That was the birth of quantum mechanics. The broken equation was a door, and the universe that lay beyond it was stranger, richer, and more beautiful than anything classical physics had imagined. There is every reason to believe that the broken equations of the Planck wall will prove to be another such door. Now, let's talk about what we do think we understand about the Planck epoch, not through confirmed theory, but through the careful extrapolations of our best current frameworks. This is where we must be transparent. What follows is informed speculation. educated inference, the frontier of human thought, not settled science. But it is remarkable frontier. At the Planck moment, the universe was not just hot and dense. It was as far as we can reason in a state where the very geometry of space-time was quantum. What does that mean? In everyday life, and even in general relativity, space-time is smooth, like the surface of a still lake, continuous, well-defined, predictable. But at the Planck-scale quantum uncertainty, the same uncertainty that makes the position of an electron fundamentally fuzzy would apply to space-time itself. The geometry of the universe would be in a state of superposition. Multiple geometries, multiple curvatures, multiple topologies, all existing simultaneously, overlapping, interfering, fluctuating wildly. This is what the physicist John Archibald Wheeler called quantum foam, and we will explore it deeply in the next part of our journey. But even the idea itself that space and time, the very stage on which all of reality performs, could be quantum mechanical, uncertain foaming, is breathtaking to contemplate. And here's what I find most extraordinary about all of this. The Planck wall is not a failure of science. It is a marker of how far science has come. A century ago, we did not know the universe had a beginning. 50 years ago, we had only just detected the cosmic microwave background, the first direct echo of the Big Bang, and confirmed the theory experimentally. 20 years ago, we discovered that the expansion of the universe is accelerating, driven by a mysterious dark energy that we still do not understand. And today, right now, tonight as you rest in the quiet, physicists are using gravitational wave detectors, space telescopes, quantum computers, and particle accelerators to probe the deep structure of reality in ways that would have seemed like science fiction to the physicists of Max Planck's era. We are not stuck. We are moving, slowly, carefully, with great humility and great ambition toward the wall, toward the moment where our maps run out, and beyond it, if we are patient and lucky and clever enough, toward the answer to the deepest question of all. Think about this for a moment, and this is something I find genuinely moving, not just intellectually interesting. Max Planck himself, when he first derived his natural units in 1899, was not thinking about the Big Bang. The Big Bang was not even a scientific concept yet. He was simply trying to clean up some untidy numbers in thermodynamics. He stumbled almost accidentally upon a set of units so fundamental that they would one day mark the edge of everything we know about the universe's birth. He could not have imagined that his quiet calculation in a Berlin lecture hall would one day define the boundary of the knowable cosmos. Science is like that. Often the most profound discoveries are not made by people who set out to make profound discoveries. They are made by people who are simply paying very close attention to small, untidy things, anomalies, inconsistencies, equations that give answers they shouldn't, a broken calculator pointing at something real. One last thought before we move forward, and I offer it gently as something to carry with you rather than something to solve. The Planck wall exists because we do not yet have a theory of quantum gravity. The search for that theory is arguably the central project of fundamental physics today. String theory loop, quantum gravity, causal, dynamical triangulation, asymptotic safety. These are not idle speculations. They are rigorous mathematical frameworks, each attempting in its own way to describe what space-time looks like when it is both quantum and gravitational. None has yet won. None has yet been experimentally confirmed. But each has taught us something. Each failed attempt has, like Planck's broken black-body formula, pointed a little more precisely at the shape of the door we are trying to open. And just beyond that door, just past the wall of silence, where our equations dissolve, lies the quantum foam, the seething, shimmering, impossible texture of space-time itself at its most fundamental. A place where space is not smooth but granular, where time is not a river but a storm, where the geometry of reality flickers and shifts a trillion times per second. That is where we are headed next, into the foam, into the shiver at the heart of existence, into the strangest landscape that physics has ever dared to imagine. Picture the surface of the ocean on a perfectly calm day. Flat, smooth, mirror still. A single unbroken sheet of silver stretching to the horizon. Now, picture that same ocean during a Category 5 hurricane. Walls of water rising and collapsing, troughs plunging 50 feet deep, spray and chaos in every direction, no surface, no continuity, no up or down that holds for more than a moment. Now, and stay with me. Here, imagine that the ocean is not water, it is space itself, and the hurricane is not wind. It is quantum uncertainty operating at the smallest scale reality allows. That hurricane, that seething, churning, formless violence at the very foundation of space-time, is what physicists call quantum foam. And it is not a metaphor. It is, as best we can currently reason, a description of what the fabric of the universe actually looks like at the Planck scale. We arrived in our last steps at the Planck wall, the boundary beyond which our equations dissolve into silence. We understood why that wall exists, because quantum mechanics and general relativity, our two greatest theories, speak different languages and cannot be translated into each other at extreme scales. Now, we are going to do something bolder. We are going to look past that wall not with confirmed equations, but with the most carefully reasoned physical intuition we have, and ask if space-time is quantum. At the Planck scale, what does it actually look like? What is the texture of reality? At its most fundamental, the answer is quantum foam. And the story of how we arrived at it is one of the most quietly radical journeys in 20th century physics. It begins as so many great ideas do with a single person sitting with an uncomfortable question. The person was John Archibald Wheeler. The question was, what happens to the geometry of space-time when you apply the uncertainty principle to it? Wheeler was one of the most remarkable physicists of the 20th century, a man who coined the terms black hole, wormhole, and it from bit, who worked on the Manhattan Project, and later became one of Einstein's closest colleagues at Princeton, and who mentored a generation of physicists, including Richard Feynman and Kip Thorne. He was, by all accounts, a man who thought not just carefully, but playfully, who believed that the deepest truths about the universe were hidden not in complexity, but in the willingness to ask simple questions with complete seriousness. In the mid-1950s, Wheeler began thinking about what quantum mechanics implied for the structure of space-time at the smallest scales. The uncertainty principle formulated by Werner Heisenberg in 1927 tells us that certain pairs of physical properties cannot both be precisely known at the same time. The more precisely you know the position of a particle, the less precisely you can know its momentum. The more precisely you know the energy of a system at a given moment, the less precisely you can know the time at which it has that energy. This is not a limitation of our instruments. It is a fundamental feature of reality. Quantum systems are in a deep sense genuinely indeterminate until they are measured. Wheeler asked, what if space-time itself, the geometric fabric of the universe, the thing that curves in response to mass and energy in Einstein's theory, is also subject to the uncertainty principle? What if the geometry of space at the Planck scale is not fixed and smooth, but fundamentally uncertain, fluctuating, indefinite, existing in a superposition of multiple geometries simultaneously? The answer he arrived at, published in a 1955 paper in Physical Review in characteristically bold and evocative language, was quantum foam. At scales above the Planck length spacetime, appears smooth. The quantum fluctuations are so small relative to the scale of ordinary physics that they are entirely invisible, like the molecular structure of a tabletop, invisible to the unaided eye, irrelevant to the cup of tea sitting on it. But zoom in to the Planck scale to distances of 10 to the negative 35 meters, and the smoothness dissolves. Space-time becomes a churning, bubbling, wildly fluctuating medium. Tiny regions of extreme curvature, miniature black holes, wormholes. Topological handles pop in and out of existence continuously spontaneously, driven by the same quantum vacuum energy that causes particles to flicker into being in empty space. The geometry itself is uncertain. Multiple geometries coexist. Space and time lose their well-defined meaning. This is not simply strange, it is conceptually revolutionary. Because everything we know about physics, everything is built on the assumption that space-time is a smooth, continuous background against which events happen. Quantum foam suggests that at the deepest level, that assumption fails. There is no smooth background. There is only the foam. Events do not happen against space-time. In some sense, space-time is made of events made of quantum fluctuations. And what we experience as the smooth geometry of space and the steady flow of time is an averaged-out large-scale illusion emerging from a substrate of inconceivable complexity and wildness. Let me offer you an analogy that I find genuinely useful here, though. Like all analogies, it is imperfect. Think about water. When you fill a glass and look at the surface, it appears smooth, continuous, featureless, a surface in the classical sense. But if you could zoom in to the molecular scale to the level of individual H2O molecules jostling and vibrating and exchanging hydrogen bonds, the surface would disappear entirely. There would be no surface, only molecules bouncing. The smoothness you see is an emergent property, a large-scale average of enormous molecular disorder. Quantum foam proposes something analogous for space-time itself. The smooth geometry we experience, the geometry that allows us to say, I am here, and that star is there, and the distance between us is this many light years, is an emergent average property of a quantum substrate that at the Planck-scale has no geometry at all in the ordinary sense. And now, here is where it gets truly extraordinary. If space-time is foamy at the Planck-scale, then the early universe, when all the energy of everything that exists was compressed into a region of Planck-scale or smaller, was entirely dominated by this foam. There was no smooth space to move through. There was no steady time to tick. There were no well-defined dimensions, no clear this direction or that direction. The universe in its first Planck instant was a quantum superposition of space-time geometries, a simultaneous existence of countless possible realities, each with different shapes, different topologies, different numbers of dimensions, all coexisting, overlapping, interfering with each other like waves on that hurricane ocean. Let that settle for a moment. The universe did not begin as a point in a pre-existing space. It began as a quantum fluctuation in which space itself was undefined, not a thing in a place, a thing that was still deciding what place meant. Now, here is a misconception that is worth addressing directly because it creates genuine confusion. People often ask if the early universe was a quantum superposition of geometries. Why did it collapse into the one geometry we observe today? This is a natural question, but it imports an assumption from ordinary quantum mechanics that may not apply here. In ordinary quantum mechanics, a superposition collapses when it is measured, when it interacts with a large classical environment. But in quantum cosmology, there is no external environment. The universe is everything. There is nothing outside it to measure it. So, the question of how the quantum universe of the Planck epoch became the classical smooth universe we observe today is genuinely open. It is one of the central puzzles of quantum cosmology. Some approaches like the decoherence program or the many worlds interpretation offer partial answers. Others remain deeply contested. We do not yet know how the foam became the lake. We know that it did. We don't yet fully know why. There is something quietly powerful in acknowledging that, not as a defeat, but as an honest account of where human understanding currently stands. The foam became the lake. The wild quantum superposition of geometries resolved somehow into the smooth space-time we navigate today. That somehow is not a gap to be embarrassed about. It is an invitation, a door still to be opened. Now, does quantum foam leave any observable signature? This is a question physicists take very seriously. After all, a concept is only scientifically useful if, in principle, it makes predictions that can be tested. And remarkably, it does, or at least might. One predicted consequence of quantum foam is a phenomenon called spacetime fuzziness, a very slight blurring of the positions and distances of objects at cosmological scales, caused by the accumulated effect of Planck-scale fluctuations over vast distances. In 2012, physicist Eric Adelberger and colleagues looked for signs of this fuzziness in data from the Fermi Gamma Ray Space Telescope, analyzing the arrival times of gamma ray photons from distant gamma ray bursts. If spacetime is foamy photons of different energies traveling across billions of light years, should arrive with tiny but detectable time differences, because higher energy photons interact more strongly with the quantum foam. The Fermi data found no such difference, placing the tightest observational constraints yet on the scale of spacetime foaminess. The result did not disprove quantum foam, but it did constrain it, telling us that if foam exists, it operates at a scale smaller or smoother than some versions of the theory predicted. That is how science works at the frontier, not with clean confirmations and refutations, but with constraints, with the steady narrowing of possibility space, one careful measurement at a time. Another potential signature of quantum foam lies in the cosmic microwave background itself, that ancient glow of radiation that we will explore in depth later in our journey. Some cosmologists believe that the quantum fluctuations of the Planck epoch, frozen and stretched by the rapid expansion that followed, are directly visible in the tiny temperature variations of the CMB. If that is true, then what we see when we map the cosmic microwave background is not just the echo of the early universe. It is in a very real sense a photograph of quantum foam, of Planck-scale fluctuations magnified to cosmic size by the expansion of space. The quantum texture of the universe's first moment printed across the entire sky. Visible if we know how to read it. Can you hold that image for a moment? The entire night sky, every direction you look, carrying the imprint of fluctuations that happened at the smallest scale, physics can describe in the first instant the time existed. The foam made cosmic. The whisper of the Planck epoch stretched across 93 billion light years of observable universe. Wheeler himself, who lived to the age of 96, continuing to think and write and wonder well into his final years, once wrote that the lesson of quantum foam was that the most important thing about space-time is not what it is, but what it does. Space-time in his vision was not a passive stage. It was an active, dynamic quantum participant in the story of the universe. It fluctuated, it tunneled, it borrowed energy from the future and returned it to the past. It was at its core alive, in a way that classical physics had never imagined. And perhaps that is the deepest lesson quantum foam offers, not just to physicists, but to anyone willing to sit with it in the quiet. What we call empty space is not empty. What we call nothing is not nothing. Even at its most fundamental, most stripped-down level, even before particles, before forces, before light, the universe was not still. It was churning with potential, foaming with the seeds of everything that would follow. The quantum foam was not a stage waiting for actors. It was itself the first act, wild, formless, seething, and from it, from that shimmering, impossible violence at the foundation of everything, something extraordinary happened next. The universe did not simply continue to foam and fluctuate. It did something that by any ordinary measure should have been impossible. It grew. Not slowly, not gradually, not in any way that ordinary physics would allow. It grew at a rate so violent, so sudden, so far beyond anything in human experience that we needed an entirely new word for it. And that word, and the breathtaking physics behind it, is where we are going next. In a fraction of a second, so small it has no name in ordinary language, the universe grew by a factor of at least 10 to the power of 78. That is not a typo. 10 to the 78. a number so large that if you tried to write it out one followed by 78 zeros, it would stretch longer than this page, longer than this room, longer than most things you could physically carry. And it happened not over millions of years, not over centuries, not even over seconds. It happened in approximately 10 to the negative 32 seconds. 100 million trillion trillionths of a second. Smaller than a Planck time by many orders of magnitude. The universe went from something smaller than a proton to something roughly the size of a grapefruit, and the seeds of every galaxy, every star, every world that would ever exist were already written inside it. This is cosmic inflation, and it is one of the most violent, most beautiful, most well-evidenced, and yet most mysterious events in the history of everything. The foam has settled just slightly just enough. The Planck epoch has given way to a universe still unimaginably hot and dense, but one where space-time has begun to take on a shape. And in that shape, something extraordinary is already stirring, a field, an energy, a tension built into the very structure of space itself, about to release. Before we go further, if these quiet explorations of the cosmos bring you comfort or curiosity or wonder, I'd love for you to stay close. A gentle tap on the like button lets me know. This kind of storytelling reaches you the way I hope it does. And if you'd like the next journey to find you softly, a subscription and a little bell will make sure it does. Arriving like a quiet knock on a dark evening whenever you need it. Now, back to the beginning of everything. Let us begin with the problem that inflation was invented to solve. Because this is important, and it is a part of the story that is often skipped. Inflation was not proposed because someone thought the universe should have expanded quickly. It was proposed because the universe, as observed, has three deep, strange features that the original Big Bang theory without inflation could not explain. And understanding these features is the key to understanding why inflation is not just a wild idea, but a scientifically necessary one. The first puzzle is called the horizon problem. Look up at the night sky. Look to the far left as far as you can see to the edge of the observable universe in that direction. Now, look to the far right to the opposite edge. Those two regions of the universe are separated by approximately 93 billion light years. They have never been in contact with each other. No signal, no light, no information of any kind has ever had time to travel between them, not in 13.8 billion years of cosmic history. And yet, when we measure the temperature of the cosmic microwave background radiation coming from both directions, it is identical to 1 part in 100,000. Both sides of the universe are at almost exactly the same temperature, 2.725 Kelvin. How can two regions of the universe that have never communicated have reached the same temperature to such extraordinary precision? In ordinary physics, two regions reach the same temperature by exchanging heat, by being in contact. But these regions have never been in contact. The standard Big Bang without inflation has no answer. It is as though you walked into a room with two thermostats at opposite ends, controlled by people who have never met and never spoken, and found them set to exactly the same temperature to 4 decimal places. Something must have coordinated them. Inflation is that something. The second puzzle is called the flatness problem. The geometry of the universe, the large-scale curvature of spacetime on cosmic scales, is extraordinarily, suspiciously flat. Not curved like a sphere, not curved like a saddle, flat like an infinite table. In the language of cosmology, the density parameter omega is equal to 1 or incredibly close to it. Now, in an expanding universe, flatness is an unstable equilibrium, like a pencil balanced on its tip. A universe that begins even slightly curved will become dramatically more curved over time. For the universe to still appear this flat after 8 billion years of expansion, it must have begun with a flatness precision of 1 part in 10 to the 60th power. That is not a coincidence. That is a fine-tuning so extreme it demands an explanation. Inflation provides any pre-inflationary curvature. However large would have been stretched so completely flat by the enormous expansion that the observable universe today would appear flat, the way the surface of a balloon inflated to the size of the Earth appears flat to an ant crawling on it. Not because it is fundamentally flat, but because it has been stretched beyond curvature's reach. The third puzzle in this one is the most elegant, is called the monopole problem. In the very early universe, according to grand unified theories of particle physics, a type of exotic particle called a magnetic monopole should have been produced in enormous quantities. A magnetic monopole is essentially a single isolated magnetic pole, a north without a south, or a south without a north. Every magnet you have ever encountered has two poles, always. But theory predicts that at the energies of the early universe, standalone monopoles should have formed abundantly. And yet we have never detected a single magnetic monopole, not one in all the observations ever made. The universe should be full of them. It appears to have almost none. Inflation solves this beautifully. If inflation occurred after the monopoles formed, the violent expansion would have diluted them so thoroughly, spreading them across a volume so enormous that the chance of finding one in the entire observable universe would be less than 1 in a trillion. They are not absent. They are simply lost in the vastness that inflation created. 3 profound puzzles, 1 elegant mechanism. That is why inflation, despite the extraordinary nature of its claims, has become part of the standard cosmological model, not because physicists find it comfortable, but because the universe seems to require it. Now, who found it? The story begins in 1979 in an office at the Stanford Linear Accelerator Center, where a young American physicist named Alan Guth was working late on a seemingly unrelated problem in particle physics. Guth was trying to understand magnetic monopoles, specifically why we don't see them, when he stumbled upon a mechanism involving a field that could cause the universe to expand exponentially fast. He worked through the mathematics, growing more and more astonished, and at some point in the small hours of that December night, he wrote 3 words in his research notebook: spectacular realization, in capital letters. He knew even then that he had found something profound. Guth's original model had a problem, a technical issue with how inflation ended, called the graceful exit problem, but it was corrected and refined shortly afterward by Russian-American physicist Andrei Linde and independently by Andreas Albrecht and Paul Steinhardt. The corrected version, called new inflation and later chaotic inflation, is the framework that has grown into the inflationary paradigm we use today. Let us now talk about what inflation actually is. Not what it does, we have seen that, but what it is. What physical mechanism drives this extraordinary expansion? The answer involves a concept called a scalar field, specifically a hypothetical field that physicists call the inflaton field. A field in physics is a quantity that has a value at every point in space. Temperature is a field. The electromagnetic field is a field. The inflaton is a field that in the very early universe was trapped in a state of very high potential energy, like a ball balanced at the top of a hill. In this state, the inflaton generates a kind of negative pressure, a repulsive force built into the structure of space itself, that drives spacetime to expand exponentially. As long as the inflaton remains in this high-energy state, inflation continues. Space doubles in size and doubles again many times per unimaginably short interval. And then when the inflaton finally rolls down the hill of its potential energy, like a ball rolling off a hilltop, inflation ends. The energy stored in the inflaton field converts into a hot, dense plasma of particles. The universe reheats. The Big Bang in its familiar form truly begins. Here is a question worth sitting with for a moment. Have you ever felt the strange vertiginous sense that something you thought was solid and fixed, a relationship, a belief, a place you called home, could simply expand in a single moment beyond all recognition? That the familiar could become vast in a way you weren't prepared for? Inflation is something like that at the level of all of reality. The universe, in the span of time too small to have a name, became incomprehensibly larger than it had been. And in that stretching, in that single silent scream of expansion, everything that came after was made possible. Now, here is the most remarkable thing inflation did beyond solving the horizon flatness and monopole problems. It took the quantum foam, those tiny Planck-scale fluctuations in the energy density of spacetime, those microscopic ripples in the inflatant field, governed by quantum uncertainty existing at scales of 10 to the negative 35 meters, and it stretched them. Stretched them from quantum scale to cosmic scale, from the smallest distances in physics to the largest structures in the universe. Think about what that means. Those tiny quantum wrinkles fluctuations so small they are in principle governed by the Heisenberg uncertainty principle were inflated into density variations across the early universe. Regions slightly denser than average, regions slightly less dense. A pattern written in quantum randomness now printed across cosmic distances. And those density variations, those slight overdensities and underdensities, became over billions of years the seeds of structure. Denser regions attracted more matter by gravity. Matter clustered, collapsed, ignited into stars. Stars gathered into galaxies, galaxies into clusters, clusters into the cosmic web. The largest structures in the observable universe, filaments of galaxies stretching hundreds of millions of light years, trace their origin directly to quantum fluctuations that occurred in the first fraction of the first second of time. The cosmic web, that magnificent structure of galaxy filaments and voids that looks when mapped uncannily like the neural network of a brain, is at its deepest origin a quantum mechanical pattern, written by uncertainty, amplified by inflation, sculpted by gravity over 13.8 billion years. You are not merely the descendant of stardust. You are the descendant of a quantum fluctuation stretched to cosmic size in a fraction of a second, 100 million trillion trillionths of a second after time began. A common misconception is worth addressing here because it comes up whenever inflation is discussed. People often ask if space expanded faster than light during inflation. Doesn't that violate Einstein's theory of special relativity? The answer is no, and the reason is beautiful. Special relativity says that nothing can travel through space faster than light, but inflation is not objects moving through space. It is space itself expanding. The galaxies, the particles, the energy, none of them moved through space faster than light. Space simply grew between them faster than light could cross it. This is a fundamental distinction in general relativity, and it means that even during the most violent expansion imaginable, no information was transmitted, no causality was violated, no signal outran the speed of light. The rule was not broken. The universe simply found a way to grow that the rule was never designed to prohibit. What is the evidence for inflation? The most powerful comes from the cosmic microwave background, the ancient glow of radiation. We will explore deeply in a later part of our journey. The CMB shows tiny temperature fluctuations whose statistical properties match with extraordinary precision the predictions of inflationary models. The fluctuations are scale invariant, nearly the same on all scales exactly as inflation predicts. This was confirmed with increasing precision by the COBE satellite. In 1992, the WMAP satellite from 2001 to 2010, and the Planck satellite named, of course, for the man whose constant marks the edge of the knowable, which released its final data in 2018. Each measurement has tightened the constraints, refined the predictions, narrowed the space of viable inflationary models. There is also the tantalizing possibility of another signature primordial gravitational waves. During inflation, quantum fluctuations in spacetime itself, gravitational waves generated by the rapid expansion should have left a specific imprint in the polarization of the CMB, a swirling pattern called B-mode polarization. In 2014, a team using the BICEP 2 telescope at the South Pole announced what appeared to be a detection of this signal. The scientific community held its breath. But subsequent analysis showed that the signal was contaminated by dust within our own galaxy, and the detection could not be confirmed. The search continues. Several experiments, including BICEP, Array the Simons Observatory, and CMB-S4, a next-generation telescope project, are currently working to detect or rule out primordial gravitational waves with far greater sensitivity. If they find them, it will be the most direct confirmation of inflation ever achieved. A whisper of gravity waves echoing from the very moment of the universe's first breath. Alan Guth, now a professor at MIT, still active, still passionate, still carrying forward the idea he scrawled in capital letters in a notebook nearly half a century ago, once described the universe as the ultimate free lunch. Everything that exists, every galaxy, star, planet, and person emerged from the quantum energy of a tiny inflating patch of space. Energy was not created from nothing. The positive energy of matter was exactly balanced by the negative energy of gravity, so the total energy of the universe is remarkably close to zero. Everything came from nothing, not because something appeared without cause, but because the nothing itself was unstable in a very precise quantum mechanical way. The free lunch was not a miracle, it was a fluctuation. And now from that fluctuation, from that extraordinary millisecond of expansion, the universe has cooled just enough, stretched just enough for something new to become possible. The foam has been flattened, the temperature has begun to fall, and in the seething plasma of energy and radiation that follows inflation, the first particles are beginning to condense. Not from nothing, but from everything from pure energy cooling into form, from fields finding their lowest energy states from the universe for the first time, beginning to have ingredients rather than simply heat. The story of matter, of how the building blocks of every star and stone and living cell first crystallized out of the primordial fire, is where we drift to next. There is a moment on cold mornings just before the world fully wakes when moisture that has been drifting invisibly through the air begins to settle, not falling, not pouring, simply appearing on blades of grass, on spider webs, on the quiet surfaces of leaves, tiny drops of water condensing from vapor into form, from invisible to visible, from nothing you could see to something you could hold on your fingertip. It happens slowly, silently, without announcement. And yet when it is done, the world is wet. The dew was always there in a sense, as vapor, as potential, as invisible moisture in the air. But now it has a shape. Now it has weight. Now it has presence. Now it is real, in a way that vapor, however present, never quite is. What happened to matter in the first microseconds of the universe was something like that. Only instead of water condensing from air, it was the fundamental building blocks of reality, quarks, electrons, neutrinos, photons condensing from pure energy, from a seething, roiling plasma of radiation, so hot that particles and antiparticles flickered in and out of existence billions of times per second. Matter began slowly and improbably to persist, to hold, to become. This is the chapter of cosmic history where the universe stopped being purely energy and radiation and started barely tentatively against what seemed like impossible odds to become something made of things. We left inflation behind, that extraordinary violent stretching of space that smoothed the universe and planted the quantum seeds of all future structure. Now in the moments that follow, the inflating field has released its energy into heat, and the universe is a fireball of almost unimaginable temperature and density. Not the Planck temperature of the very first instant that has already fallen by orders of magnitude, but still trillions upon trillions of degrees. A temperature at which the distinction between matter and energy is not yet meaningful. Everything is radiation. Everything is heat. Particles appear and annihilate so rapidly that no individual particle persists long enough to be called a particle in the ordinary sense. The universe is a plasma, but not like any plasma we have on Earth. A plasma so dense, so energetic, so opaque that light itself cannot travel more than a tiny fraction of a millimeter before being absorbed and re-emitted. And in this plasma, something momentous is about to happen. Let us begin with quarks. Quarks are the fundamental constituents of protons and neutrons, the particles that make up the nuclei of every atom in the universe. In the very early universe, at temperatures above approximately 2 trillion Kelvin, quarks exist freely, not bound inside protons or neutrons, but moving as independent particles through the quark-gluon plasma. This state of matter, the quark-gluon plasma, is so extreme that it has only ever been recreated on Earth in the most powerful particle accelerators ever built. At the Large Hadron Collider at CERN, physicists can create tiny fleeting droplets of quark-gluon plasma by colliding gold or lead nuclei at nearly the speed of light. These droplets exist for approximately 10 to the negative 23 seconds before cooling and fragmenting back into ordinary particles. They are in a very real sense the hottest, densest objects ever created by human beings. Tiny recreations of the universe's infancy, lasting less time than it takes light to cross a single proton. Now, here is something remarkable about those LHC experiments. When physicists first created quark-gluon plasma and studied its behavior, they expected it to behave like a gas, a collection of particles moving independently, colliding, rebounding. Instead, it behaved like a liquid. A perfect liquid, in fact, a fluid with a viscosity so close to zero that it flows with almost no internal friction. The closest natural analog we have is liquid helium cooled to near absolute zero, which becomes a superfluid and flows without any resistance whatsoever. The quark-gluon plasma of the early universe was something like a superfluid of fundamental particles, an almost frictionless sea of quarks and gluons flowing and rippling in response to the quantum fluctuations that inflation had stretched across the universe. Those ripples matter enormously. The density waves in the quark-gluon plasma sound waves, essentially, but at a scale and energy beyond anything ordinary, propagated outward from regions of higher density driven by the pressure of the plasma itself. These acoustic waves, called baryon acoustic oscillations, left an imprint on the distribution of matter across the universe that we can still measure today in the large-scale structure of galaxy surveys. The ringing of the primordial plasma frozen into the cosmic web, the first sound the universe ever made, still echoing in the positions of galaxies separated by hundreds of millions of light years. Now, as the universe continued to expand and cool, something decisive happened at around 1 microsecond after the Big Bang. The temperature dropped below approximately 2 trillion Kelvin, and quarks could no longer exist freely. The strong nuclear force carried by particles called gluons and responsible for binding quarks together became strong enough to permanently confine quarks into composite particles. 3 quarks bound together into protons and neutrons. Quark-antiquark pairs bound together into mesons and other short-lived particles. The free quarks were gone. In their place, the first hadrons, the first protons, the first neutrons. This transition is called the QCD phase, transition QCD, standing for quantum chromodynamics, our theory of the strong nuclear force. It is in a very real sense the moment when the universe first had ingredients in any recognizable sense of the word. Not fundamental fields, not quantum foam, not pure radiation, but something a chemist, if any, could have existed, might have pointed at and said, that is a particle, that is a thing. And yet there was a problem, a deep, fundamental, existentially troubling problem. For every particle of matter that formed, a particle of antimatter also formed. Protons and antiprotons, neutrons and antineutrons, electrons and positrons, created in equal numbers by the symmetry of the laws of physics, because every process that creates a particle creates its antiparticle counterpart, and matter and antimatter, when they meet, annihilate, completely, violently, converted back into pure radiation. If matter and antimatter had truly been created in exactly equal numbers, if the symmetry had been perfect, they would have annihilated each other completely. every proton destroyed by every antiproton, every electron by every positron, the universe would have been left with nothing but radiation. A universe of pure light expanding into darkness. No atoms, no stars, no planets, no life, no one to wonder about any of it. And yet, here you are, made of matter, breathing, thinking, existing. How? The answer is one of the deepest unsolved mysteries in all of physics, but we have strong clues, and those clues involve a concept called CP violation. CP stands for charge parity symmetry. The idea is this: the laws of physics at a fundamental level should be symmetric under the simultaneous reversal of charge and the reversal of spatial orientation. In other words, if you replaced every particle with its antiparticle and mirrored the universe in a spatial reflection, the physics should look the same. For a long time, physicists assumed this symmetry was perfect. Then, in 1964, in a landmark experiment at Brookhaven National Laboratory on Long Island, physicists James Cronin and Val Fitch discovered something extraordinary. Certain particles called kaons decayed in ways that violated CP symmetry. They did not behave identically to their antimatter counterparts. The violation was tiny, a difference of less than 1%. But it was real, and it was measurable. Cronin and Fitch were awarded the Nobel Prize in Physics in 1980 for this discovery, and it opened the door to understanding why we exist. In 1967, the Soviet physicist Andrei Sakharov, one of the creators of the Soviet hydrogen bomb, who later became one of the most prominent human rights advocates of the 20th century, and whose story is one of the most remarkable in the history of science, outlined 3 conditions necessary for a universe to generate more matter than antimatter from an initially symmetric state. These conditions are now called the Sakharov conditions. They include processes that violate baryon number conservation, the violation of CP symmetry, and a departure from thermal equilibrium. All 3 are thought to have been present in the early universe. The details of exactly how they combine to produce the matter excess we observe today is still being worked out, but the framework Sakharov provided remains more than 50 years later, the standard starting point for all theories of matter, antimatter asymmetry. The excess of matter over antimatter scientists believe was approximately 1 part in a billion. For every billion antiprotons in the early universe, there were 1 billion and 1 protons. The billion pairs annihilated, the 1 proton remained, and from those surviving protons and neutrons, those 1 in a billion survivors of the great annihilation, everything that exists was built. Every star, every ocean, every mountain, every cell, every thought you have ever had. You are the descendant of a rounding error, a 1 in a billion survivor of a cosmic collision between matter and antimatter that ended almost entirely in mutual annihilation. Sit with that for a moment. Because it is not a discouraging thought, it is, I think, one of the most quietly astonishing facts in the history of knowledge. Your existence and the existence of everything you have ever known or loved rests on a tiny fundamental asymmetry in the laws of physics that we still do not fully understand. A hairline crack in the mirror of matter and antimatter. A whisper of difference written into the deepest equations of reality. Without it, the universe would be dark and empty and silent forever. With it, this. There is one more transition to explore in this part of our journey, and it is perhaps the most quietly profound of all. At about 10 microseconds after the Big Bang, as protons and neutrons were forming from quarks, another field made its presence felt in a way it never had before. A field that permeates all of space even today, even now, in the room where you are resting. It is called the Higgs field. The Higgs field was proposed in 1964 by several physicists, including Peter Higgs at the University of Edinburgh, and independently by François Englert and Robert Brute in Brussels. Their idea was that space is not empty. It is filled with a field, and particles moving through it experience a kind of drag, a resistance proportional to how strongly they interact with the field. That resistance, that interaction, is what we experience as mass. Before the Higgs field switched on, before the universe cooled enough for the field to settle into its lowest energy state, fundamental particles had no mass. They moved at the speed of light like photons do. The universe was a place where nothing could be still, nothing could gather, nothing could hold. When the Higgs field settled, when it underwent what physicists call spontaneous symmetry, breaking cooling into a non-zero value throughout all of space, particles that interact with it slowed down. They acquired mass. They could now be bound together by forces. They could cluster. They could form structure. The Higgs field was confirmed experimentally on July 4th, 2012, with the detection of its associated particle, the Higgs boson, at the Large Hadron Collider at CERN. It was announced by CERN Director General Rolf Hoyer with the words, "I think we have it." In the auditorium, Peter Higgs, then 83 years old, quietly wiped a tear from his eye. He had waited 48 years for that moment. Consider what you are in light of all of this. You have mass, the sensation of weight, of solidity, of presence, because particles in your body interact with a field that settled into its lowest energy state a fraction of a second after the Big Bang. Your heaviness is ancient. Your substance is a consequence of a phase transition that happened before the first atom, before the first star, before the universe was even a second old. And now, from that moment of the Higgs field, settling from the first protons and neutrons, forming from quarks, from the survival of 1 in a billion particles of matter against a sea of annihilation, the universe has its ingredients: protons, neutrons, electrons, photons, neutrinos, the building blocks of everything. But having ingredients is not the same as having structure. The next question is, how do those ingredients combine? How do protons and neutrons come together to form the first atomic nuclei? And the answer unfolds in the most extraordinary 3 minutes in the history of chemistry. A moment so brief, so precise, so perfectly balanced, that the slightest deviation in any direction would have produced a universe with no stars, no planets, and no story worth telling. Those 3 minutes are where we are headed next. 3 minutes. That is all the time the universe had. 3 minutes, roughly the time it takes to brew a cup of tea, to walk from one end of a quiet street to another, to let a thought drift through your mind and settle to forge the atomic nuclei that would become every star, every ocean, every living cell that has ever existed. 3 minutes. After that, the window closed, the temperature dropped too low, the density thinned too far, and the universe moved on, carrying inside it a precise locked recipe that it would not revisit for hundreds of millions of years. The proportions written in those 3 minutes, roughly 75% hydrogen, 25% helium, with traces of lithium and beryllium, are still there today, in the oldest stars in our galaxy, in the gas clouds between the stars, in the primordial light of the most distant quasars that our telescopes have ever reached. Unchanged, intact, preserved across 13.8 billion years, like a message written in the first fire, still legible in the last starlight. And when astronomers went out and measured those ratios in the oldest, most pristine corners of the observable universe, they matched, precisely, exactly as predicted. That match is one of the most powerful confirmations that the Big Bang Theory is not just a compelling story, but a description of something real. We arrived here at the threshold of the first second, with matter having just claimed its unlikely foothold in the universe. Protons and neutrons fresh from the quark-gluon plasma. The Higgs field settled, mass acquired, particles persisting. The great matter-antimatter annihilation behind us with its 1 in a billion survivor ratio, giving matter the slimmest, most improbable of margins. Now, the universe is approximately 1 second old. The temperature is around 10 billion Kelvin. And the 3-minute clock, has just started. This process is called Big Bang nucleosynthesis. It is the story of how the universe first built atomic nuclei. the cores of atoms made of protons and neutrons bound together by the strong nuclear force. And it is a story of extraordinary precision, extraordinary balance, and hidden inside it, extraordinary human drama. Let us begin with the physics told simply. At 1 second after the Big Bang, the universe contains protons and neutrons in a ratio of approximately 7 to 1. 7 protons for every neutron. This ratio is not arbitrary. It is set by the balance of weak nuclear force interactions that converted protons and neutrons into each other during the first second of the universe's life. When the temperature dropped below about 10 billion Kelvin, those conversion reactions became too slow to keep up with the expansion, and the ratio froze, 7 to 1. That number is going to matter enormously. Between about 1 second and 3 minutes after the Big Bang, as the temperature continued to fall from 10 billion to about 1 billion, Kelvin conditions became right for protons and neutrons to fuse together. Not into full atoms. Electrons are still free. The temperature is still far too high for electrons to be captured into orbits. But into nuclei. A proton and a neutron fuse to form deuterium heavy hydrogen. 2 protons and 2 neutrons fuse to form helium-4, the most stable light nucleus. Tiny amounts of tritium-helium, 3 lithium-7 also form. And then, at about 3 minutes, it stops. The temperature has fallen below the threshold for nuclear fusion. The density has thinned enough that collisions between nuclei become rare. The universe expands past the point where nucleosynthesis can continue. Whatever has been made, has been made. The result of those 3 minutes, given the 7 to 1 proton to neutron ratio, is almost exactly 75% hydrogen by mass and 25% helium, with traces mere parts per billion of deuterium and lithium. And that is the composition of the universe as it existed before the first star ever lit up. A universe of almost pure hydrogen and helium, waiting in darkness for gravity to gather it and compress it and ignite it into the first stellar fires. Now, let me tell you the human story behind this science, because it is one of the most colorful and improbable in the history of physics. In 1948, a young graduate student named Ralph Alpher was working on his doctoral dissertation at George Washington University under the supervision of the brilliant, eccentric Russian-American physicist George Gamow. Gamow was a man of enormous energy and even larger sense of humor, famous for practical jokes, witty limericks, and an absolute refusal to take himself too seriously. Alpher and Gamow were working on a paper describing how the light elements could have been synthesized in the hot early universe. Essentially, they were developing the first detailed theory of Big Bang nucleosynthesis. The paper was nearly complete. It needed to be submitted. And Gamow, looking at the author list, Alpher and Gamow had an idea. The names he noticed sounded like the first 2 letters of the Greek alphabet Alpha and Gamma. What if he added a third author to complete the sequence Alpha, Beta, Gamma? The obvious candidate was Hans Bethe, one of the most prominent nuclear physicists in the world, the man who had won the Nobel Prize for explaining how stars generate energy, who had in fact absolutely nothing to do with this paper. Gamow wrote to Bethe and asked if he would allow his name to be added. Bethe, amused, agreed. And so the paper, The Origin of Chemical Elements, was published in Physical Review on April 1, 1948, under the names Alpher, Bethe, and Gamow. Alpha, Beta, Gamma, April Fool's Day, a paper about the origin of everything published with a built-in pun. Ralph Alpher, whose actual doctoral work was being somewhat overshadowed by the joke attached to it, was reportedly not entirely amused. He was a young, serious scientist trying to establish his reputation, and the presence of the famous Bethe on his paper made it difficult for people to assess exactly what Alpher himself had contributed. He spent much of his later career working to receive proper credit for his genuine foundational contributions to nucleosynthesis theory. He died in 2007, still feeling that his work had never been fully recognized in proportion to its importance. It is a quiet, bittersweet lesson hiding inside one of the greatest scientific papers of the 20th century. Brilliance does not always guarantee recognition, and sometimes the most profound work is done by people whose names are not the ones the history books remember first. The Alpha Beta Gamma paper predicted not only the light element abundances, but also in a remarkable separate paper by Alpha and Robert Herman, that same year that the hot early universe should have left behind a residual glow of radiation, now cooled to a temperature of a few degrees, above absolute zero, filling all of space uniformly. They predicted the cosmic microwave background 16 years before it was accidentally discovered. In 1965, Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs in New Jersey, were calibrating a large horn antenna, originally built for satellite communications. They found an irritating, persistent background noise coming from every direction in the sky equally that they could not explain and could not get rid of. They even climbed into the antenna and cleaned out a pair of pigeons that had nested inside it, and their droppings, which Wilson delicately described in the official report as white dielectric material, thinking the birds might be the source of the interference. The noise remained. They eventually learned through a colleague at Princeton that they had detected the cosmic microwave background, the cooled afterglow of the Big Bang itself, the direct observational confirmation that the universe had once been hot, dense, and uniform. They won the Nobel Prize in Physics in 1978. Alpha and Hermann, who had predicted the CMB 17 years earlier, did not share it. Science, like the universe itself, is not always perfectly fair, but the work endures. The prediction was real, the discovery was real, and the CMB, that faint cold glow of ancient radiation, has become the single most important piece of evidence we have for the nature of the early universe. Now, back to the nucleosynthesis itself. There is a detail in the 3-minute story that is worth dwelling on, because it illustrates the extraordinary fine-tuning of the universe in a way that feels almost personal. The ratio of neutrons to protons at the start of nucleosynthesis, 1 to 7, is not a number that could have been very different without dramatically changing the outcome. If there had been slightly more neutrons relative to protons, more helium would have formed, and less hydrogen. With too little hydrogen, the universe would have formed very few stars of the type that can support stable, long-burning solar systems. If there had been slightly fewer neutrons, almost no helium would have formed, and without helium as a stepping stone, the heavier elements that stars eventually produce would have been far harder to generate. The universe in either case would have been profoundly different. Perhaps too different for complexity, for chemistry, for biology, for anything like us to arise. This is not a claim that the universe was designed for us. That is a philosophical question, not a scientific one, and it lies beyond what physics can answer. But it is a fact, a genuine, measurable, remarkable fact, that the physical constants of the universe as they existed in the first seconds of time are calibrated in ways that permitted the emergence of complexity. Whether that calibration is a coincidence, a consequence of some deeper principle, an artifact of the anthropic principle, the observation that we can only exist in a universe capable of producing us or something else entirely is one of the most fascinating open questions in all of science. Here is something I find quietly wonderful about Big Bang nucleosynthesis as a chapter in the story of the cosmos. It is the moment when the universe first acted like a chemist. Not a physicist. The Planck epoch and inflation are pure physics, pure geometry, pure energy. But nucleosynthesis is the first moment of combination, the first moment of building, a proton and a neutron reaching across the void, drawn by the strong nuclear force and holding on. The first bond, the first structure. The first hint that this universe was not content to remain a sea of unattached particles. It wanted to make things. It was practicing. Those first nuclei, deuterium, helium, lithium, were not yet atoms. They were naked nuclei still bathed in a plasma so hot that no electron could remain bound to them. They would remain that way for a long time, waiting in the hot, dense, luminous fog of the early universe for hundreds of thousands of years until the universe had cooled enough for electrons to finally settle, to finally be captured, to finally complete the atom. That moment, the moment of completion, when the universe first became transparent, when light first traveled freely, when the cosmic microwave background was released, is waiting just ahead of us, in the long, quiet, dark age of the universe that stretches between the end of nucleosynthesis and the birth of the first star. A darkness more profound and more beautiful than anything we have explored so far. Let's drift into it. For 380,000 years, the universe was on fire. Not the fire of burning wood or erupting volcanoes. Those are tame, ordinary things, barely warm by comparison. This was a fire of a different kind entirely. A fire so complete, so total, so all-encompassing that it filled every point in space simultaneously. There was no darkness anywhere in the universe, not a single shadow, not a single corner of quiet. Because light photons, the particles of electromagnetic radiation, could not travel more than the width of a few atoms before being absorbed and re-emitted by the plasma that filled everything. The universe was opaque, a luminous, roiling, impenetrable fog of radiation and matter so dense that it trapped its own light, the way a thick cloud traps the sun from the inside. And then, at 380,000 years after the Big Bang, something happened that changed everything. Not with a sound, not with a flash, with a silence. The most important silence in the history of the cosmos. The universe cleared, and for the first time, light was free. The darkness that followed the true darkness, the first real darkness the universe had ever known, lasted for hundreds of millions of years. No stars, no galaxies, no light of any kind streaming across the void. Just hydrogen and helium drifting in the cold, slowly gathering under gravity's patient, invisible pull. This epoch from recombination to the ignition of the first stars is called, with a kind of haunting accuracy, the cosmic dark age. We drifted in our last step through the 3-minute universe, through the extraordinary brevity of Big Bang nucleosynthesis, through the first bonds between protons and neutrons, through the human story of alpha and gamma, and the paper that predicted the afterglow of creation years before anyone found it. Now hundreds of thousands of years have passed in the story. The nuclei are their hydrogen-helium traces of lithium, but they are still naked, still ionized, still stripped of their electrons. Because for all this time, the universe has been too hot for electrons and nuclei to hold together. Any electron that drifts close to a proton is immediately knocked away by a high-energy photon. The universe is a plasma, and in a plasma light cannot travel freely. It bounces and scatters and bounces again, like sunlight diffusing through fog. Every direction looks the same, bright hot and impenetrable. And then, at 380,000 years, the temperature finally drops below approximately 3,000 Kelvin. That is still hotter than the surface of most stars. But it is cool enough for something profound. It is cool enough for electrons to slow down. Cool enough for the electrical attraction between a proton and an electron, that ancient fundamental pull between opposite charges, to finally gently win. Electrons settle into orbits around nuclei. Hydrogen atoms form. Helium atoms form. For the first time in the history of the universe, there are complete atoms. Not ions, not plasma. Atoms stable, neutral, electrically invisible to photons. And because neutral atoms interact with light far less than ions do, the universe becomes almost instantly, in cosmological terms, transparent. The photons, all those countless billions of photons that had been bouncing and scattering through the plasma for 380,000 years, are suddenly free. They stream outward in every direction, unimpeded, unscattered, traveling at the speed of light across an ever-expanding universe that will never again be opaque to them. That moment is called recombination, a slightly misleading name since electrons were combining with nuclei for the first time, not recombining. The physicist who coined the term apparently knew this, But the name stuck the way so many slightly imprecise names do in science because no one bothered to correct it before it became universal. The light released at recombination, that first ancient flood of free photons, is still traveling today. It has been traveling for 8 billion years. In all that time, as the universe expanded, it has been stretched, its wavelength lengthened, its energy reduced, cooled from 3000 Kelvin to just 2.725 Kelvin, just barely above absolute zero. It now peaks in the microwave range of the electromagnetic spectrum, and it fills the entire sky uniformly in every direction. This is the cosmic microwave background, the CMB, the oldest light in the universe, the afterglow of recombination, the photon echo of the moment the universe first became transparent. Think about what that means for you tonight. Right now, as you rest, microwave photons from 13.8 billion years ago are passing through you, through the walls of your room, through the earth beneath you, through everything in every direction without pause. You are immersed at this very moment in the oldest light in the universe. You are bathed in the afterglow of creation. It does not warm you. It is far too cold and diffuse for that. But it is there, ancient, constant, arriving from every direction, equally from the edge of what we can ever observe from the last surface of the universe's own infancy. Now, here is where we encounter one of the most spectacular misconceptions about the CMB, and correcting it opens a door to something genuinely beautiful. Many people, when they first learn about the cosmic microwave background, imagine it as a distant shell, a sort of cosmic wallpaper sitting somewhere far away at the edge of the observable universe, as though the universe has a surface you could point to and say there, that is where the CMB comes from. But that is not quite right. The CMB does not come from a distant location in the universe as it is today. It comes from a distant moment in the universe's history, a moment when the entire universe everywhere was at the temperature of recombination. What we observe as the CMB is the light from that moment reaching us now from regions of the early universe that are currently located about 46 billion light years away, beyond which the expansion of space means no light from those regions has had time to reach us yet. It is not a wall, it is a horizon, a temporal horizon, the furthest back in time that light will ever let us see. Beyond it in time, not space, lies the plasma era, the nucleosynthesis, the Planck epoch. All the things we have explored in the earlier parts of this journey, the CMB is the last scattering surface, the final moment before transparency, and everything before it is by the nature of light itself hidden from direct observation. We can only infer what came earlier. We cannot see it. And yet, the CMB is not uniform. It is almost uniform. To one part in 100,000, it is the same temperature in every direction. But in those tiny deviations, those minute ripples of slightly warmer and slightly cooler patches mapped with extraordinary precision by satellites including COB, EWMAP, and Planck, lies the entire future history of the universe. Those temperature fluctuations are the direct imprint of the density variations we discussed when we talked about inflation. The quantum fluctuations of the Planck epoch, stretched to cosmic scale, now baked into the temperature map of the last scattering surface. Denser regions of the early plasma were slightly warmer. Less dense regions were slightly cooler. And those temperature differences, those 1 in 100,000 variations, were the seeds. Over hundreds of millions of years of gravitational collapse, those slightly over-dense regions attracted more matter. More matter attracted more matter. The over-densities grew, collapsed further, heated, and eventually ignited. The first stars were born in the densest peaks of a temperature pattern, etched into the CMB. When you look at a map of the cosmic microwave background, that beautiful speckled oval of blue and red patches that has graced the covers of science journals and textbooks, you are not looking at an abstract diagram. You are looking at the blueprint of the universe, the original architectural drawing in light of everything that would ever exist. Here is a question that I find genuinely stirring. If the CMB is the oldest light we can ever observe, and if that light carries within it the pattern that determined where every galaxy and star would form, then in a very real sense, the fate of every star system, every planet, every ocean, every moment of life that has arisen in this universe was already written, at least statistically, in the temperature map of the plasma at 380,000 years after the Big Bang. Does that feel deterministic to you? Constraining perhaps? Or does it feel as it does to me, like something closer to wonder, that the universe at its very beginning was already patterned in a way that made complexity possible? That the quantum tremors of the Planck epoch were not just random noise, they were the signature of a universe that could become interesting. The moment of recombination also marks the beginning of the epoch that cosmologists call the cosmic dark age. And it is worth spending a moment in the dark because it is a remarkable and underappreciated part of the story. After the CMB photons streamed away, the universe was left in darkness. Not plasma darkness, the opaque luminous fog of the early universe, but true darkness. The darkness of a universe that has no stars yet. Hydrogen and helium, neutral and cold, distributed in the faint pattern written by inflation, and preserved in the CMB, began to drift together under gravity. But gravity is slow. It works patiently across enormous distances over enormous stretches of time. For approximately 150 to 800 million years, the estimates vary, and the exact boundary is one of the things astronomers are working to pin down. More precisely, the universe had no sources of light at all. No stars, no quasars, no galaxies. Just gas, and gravity, and time, and the slow, invisible accumulation of matter into the first tendrils of what would eventually become the cosmic web. This is the era that astronomers call the Dark Ages, and penetrating it observationally is one of the great challenges of modern astronomy. Because the Dark Ages by definition produced no light or almost none, with the exception of the faint 21-centimeter emission of neutral hydrogen, they are extremely difficult to observe directly. The James Webb Space Telescope launched in December 2021 and now operating 1,000,000 miles from Earth at the second Lagrange point of the Sun-Earth system is specifically designed, among other goals, to peer as close to this epoch as possible, to find the earliest galaxies, the first quasars, the first stars. To push back our observational horizon as close to the edge of the Dark Ages as the laws of physics allow. Its first deep field images, released in July 2022, revealed galaxies existing only 235 million years after the Big Bang, far earlier than astronomers expected. Some of those earliest galaxies are unexpectedly large and bright, challenging our models of how fast the first structures could form. The universe, it seems, built its first cities faster than we had anticipated, and in doing so, it has given astronomers a puzzle, a beautiful, productive, science-driving puzzle that will take years or decades to fully resolve. The Dark Ages are not entirely dark to us. They are beginning slowly and in fragments to be illuminated not by the stars within them, but by the instruments and ingenuity of people who refuse to accept that any chapter of the universe's history is permanently beyond our reach. There is a moment in the transition out of the Dark Ages called Ryanization, when the first stars and quasars began to emit ultraviolet radiation, powerful enough to ionize the neutral hydrogen surrounding them. Gradually, over hundreds of millions of years, the intergalactic medium, the gas between the galaxies, was ryanized, made transparent to ultraviolet light once more. The universe went from dark to lit, not in a single moment, but in a slow dawn, the longest sunrise in history, lasting hundreds of millions of years, as the first lights flickered on, one by one, across the vast dark stage of the cosmos. That sunrise, that ryanization, marks the end of the cosmic dark ages and the beginning of the universe we can more easily recognize. A universe of stars and galaxies and light. A universe moving slowly but unmistakably toward complexity, toward planets, toward chemistry, toward life, toward the moment 13 billion years later, when a creature on a small rocky world would lie quietly in the dark and try to trace the path of its own existence all the way back to the beginning of time. That creature is you, and the path leads here to one last place, one final moment we have been building toward across this entire journey. Not a place in space, not an event in the past, but a truth about the present, about what it means to be made of the universe, to carry its history inside you, and to understand at last the echo that has been reaching you all along. That is where we are going now, into the closing, into the quiet that holds everything. You are still here. After all of that, after the Planck wall and the quantum foam, after the inflation that screamed the universe into existence, after the 3 minutes that forged the nuclei of every atom, after 380,000 years of opaque luminous fire, and then the long, patient darkness that followed you, are still here, listening, breathing, made of the very things we have been tracing all night back to their impossible origin. That is not a small thing. That is arguably the most remarkable thing in the observable universe. Let us take one last quiet walk through what we know, not to summarize summaries or for textbooks, but to feel just for a moment the full weight and the full wonder of the story we have been inside together. The universe began or transitioned or emerged or simply became describable at the Planck epoch. 10 to the negative 43 seconds, a temperature of 10 to the 32 Kelvin, a density so extreme that the entire observable universe, all 93 billion light-years of it, was compressed into a volume smaller than a single proton. At that moment, the four forces of nature, gravity, electromagnetism, the strong nuclear force, the weak nuclear force, were unified into a single superforce whose nature we have not yet been able to describe. The geometry of space-time was quantum. Space itself was a foam fluctuating uncertain, existing in a superposition of geometries that defies any ordinary image. This was not chaos in the colloquial sense. This was the universe operating by rules we have not yet found the language to write. Then, inflation, the extraordinary, almost incomprehensible expansion that took a Planck-scale seed and stretched it to the size of a grapefruit in a fraction of a second. An expansion that ironed the universe flat. That diluted the exotic relics of the earliest moments. That stretched quantum fluctuations to cosmic scales and planted in the fabric of space the seeds of every structure that would ever form. The seeds of you. Then the first particles, quarks condensing from energy, the Higgs field, settling mass appearing in the universe for the first time. The great annihilation of matter and antimatter, and the 1 in a billion survival rate that left just enough matter standing for the universe to have anything at all to work with. Then 3 minutes of nucleosynthesis, protons and neutrons fusing in the dying heat of the early universe, writing a recipe in the ratio of hydrogen to helium that we can still read today in the oldest stars. Then 380,000 years of luminous opacity, followed by the release of the cosmic microwave background, that ancient light still traveling, still arriving, passing through you right now as you rest. And then the long darkness, the patient gathering of gas under gravity, the slow ignition of the first stars, enormous, brilliant, short-lived giants, burning elements heavier than hydrogen and helium into the universe for the first time. Carbon, oxygen, nitrogen, iron, the building blocks of chemistry, of biology, of you. When those first stars died, and they died violently in supernova explosions that briefly outshone entire galaxies, they seeded the interstellar medium with the elements they had made. The gas clouds that formed the next generation of stars were richer, more complex, more capable of producing planets with the chemistry to support something that had never existed in the universe before: life. Now, here is something I want you to sit with. Really sit with in the quiet of wherever you are right now. The carbon in your body was forged inside a star that died before our sun was born. The iron in your blood was produced in a supernova explosion that occurred billions of years ago in a galaxy that may no longer exist. The oxygen you are breathing right now on this exhale was synthesized in the nuclear furnace of a massive star that ended its life in fire and light long before the Earth had cooled enough to have oceans. You are not made from the Earth. You are made from dead stars. You are in the most literal and precise scientific sense stardust. The universe recycled its own ashes and made something that could wonder about the recycling. The astronomer Carl Sagan, whose ability to find the human heart inside the most inhuman scales of the cosmos has never been surpassed, wrote in his 1980 book Cosmos that we are a way for the universe to know itself. He was not being poetic in the dismissible sense. He was being precise. Because here is the fact: the universe at the Planck epoch had no knowledge of itself. It was pure energy, pure geometry, pure potential. It had no observer, no witness, no awareness of any kind. And yet, 13.8 billion years later, here you are, a structure assembled from the cooling remnants of that original fire complex, enough to reconstruct in your mind the conditions that existed before you were possible. You are the universe's way of looking back at its own beginning. And the looking is not incidental. It is perhaps one of the most extraordinary things the universe has ever done. Let me share with you one last piece of data, and it is, I think, one of the most quietly astonishing numbers in all of science. In 2013, the Planck satellite, that extraordinary instrument named for the physicist, whose constant marks the edge of the knowable, released its most precise map of the cosmic microwave background ever produced. It measured the temperature of the CMB to a precision of 1 part in a million across the entire sky. It found fluctuations, those tiny ancient ripples we have been talking about all night, with an amplitude of approximately 1 part in 100,000. From those fluctuations, cosmologists extracted the most precise measurements ever made of the composition of the universe: 4.9% ordinary matter atoms, the stuff you and I are made of; 8% dark matter, a mysterious substance that interacts gravitationally but does not emit or absorb light, whose nature remains entirely unknown; 68.3% dark energy, an even more mysterious component driving the accelerating expansion of the universe, whose physical origin is one of the deepest open questions in all of physics. So, here is the humbling truth delivered gently but honestly. Everything you have ever seen, every star, every planet, every ocean, every face you have ever loved, every book, every song, every dream you have ever had, all the ordinary matter that has ever existed, the atoms that make up every galaxy, every nebula, every living creature that has ever breathed on any world, constitutes just 4.9% of the total energy content of the universe. We are a small ingredient in a recipe we don't yet understand. Visible matter is the minority. The majority of the universe is dark, unknown, unmapped, felt only through its gravitational effects, a great silent presence surrounding everything we can see. And yet, and here is where I find something not discouraging but deeply moving, that 4.9% was enough. Enough to make stars, to make chemistry, to make a small blue world orbiting an unremarkable star in the outer arm of an ordinary spiral galaxy. Enough to make the conditions for something as improbable and as precious as a mind that asks questions. Do you ever wonder, and this is a genuine question, not a rhetorical one, what it means that we can understand any of this? That the same universe that began in a state of pure, featureless mathematical chaos at the Planck epoch has produced, after 8 billion years, organisms capable of reconstructing that chaos using mathematics observation and the careful accumulation of knowledge. The physicist Eugene Wigner called it the unreasonable effectiveness of mathematics, the strange, inexplicable fact that abstract mathematical structures invented by human minds for purely intellectual reasons turn out to describe the physical universe with extraordinary precision. There is no obvious reason why this should be true, and yet it is. The Planck length, the inflationary spectrum, the CMB power spectrum, the baryon acoustic oscillations, all of them describable precisely and beautifully in the language of mathematics. The universe is at some deep level mathematical, and we are mathematical enough to read it. Here is what I keep returning to at the end of a journey like this one: the Big Bang at the Planck scale. What did it really look like? We have explored everything we currently know: quantum foam, inflation, particle creation, nucleosynthesis, recombination, the dark ages and their slow luminous end. And the only honest answer is that we do not yet fully know. The Planck wall still stands. The question of quantum gravity remains open. The nature of dark matter and dark energy remains one of the great unsolved problems of 21st century science. The reason for the matter, antimatter asymmetry for your existence, is not yet definitively explained. But here is what we do know. We know the universe had a beginning, or something indistinguishable from one. We know it was hot and dense and expanding. We know it produced matter and structure and light. We know the light from its infancy is still here, still traveling, still arriving, still gently passing through everything, including you, right now. We know the journey from quantum foam to conscious observer took 13.8 billion years. We know that journey happened because you are the proof of it. And somewhere in a laboratory and an observatory at a desk covered in equations at 2 in the morning, someone is working on the next piece. Working on the theory of quantum gravity that will finally let us see past the Planck wall. Working on the experiment that will detect or rule out primordial gravitational waves. Working on the telescope that will find the first stars and pull them at last out of the darkness. Working on the question that will reframe everything we think we know about the first second of time. The story is not finished. It will never perhaps be entirely finished. And that more than any single fact we have uncovered tonight is the most beautiful thing about it. The universe is still becoming. And so, in your own quiet way, are you? Carl Sagan once said, and I return to this often because it is precisely true: the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. Tonight, in this long, drifting journey through the first moments of everything you have done exactly that. You have been the universe knowing itself, tracing the path from the Planck epoch, from quantum foam and infinite temperature through inflation, through the first particles, through the great fires of nucleosynthesis, through the ancient light of the CMB, through the long, patient dark, all the way to this moment, this breath, this quiet, this wondering. Every atom in your body has been on a 13.8 billion year journey to arrive at this exact moment. That is not a metaphor. That is nuclear physics and stellar evolution, and the expansion of space-time, and the patient work of gravity, measured and confirmed and written in the oldest light in the universe. You are the universe's longest project, its most improbable outcome, its most recent form of self-awareness. And you spent part of your evening thinking about it. That I think is something worth being quietly, deeply glad about. Thank you. Thank you for traveling with me tonight through the Planck wall, through the quantum foam, through the inflation that stretched everything into being, through the 3 minutes that forged the atoms in your bones. Thank you for staying with the questions that have no easy answers. Thank you for the kind of curiosity that doesn't need a conclusion to feel satisfied, that can rest comfortably in the not yet knowing. That is, I believe, the most scientific disposition of all. If this journey brought you something wonder or calm, or simply the good tiredness of having thought about something larger than the day, I am so glad it found you. If you have been resting with us for the first time tonight, you are warmly welcome here. And if you have been here before, it means more than I can easily say. A gentle tap on the like button, if you felt anything tonight, helps this kind of quiet science find the people who need it. And if you'd like the next journey to arrive softly whenever the evening calls for it, a subscription will make sure it does. The next story is already waiting. Another question. Another ancient mystery. another corner of the universe that turns out on closer inspection to be about us. I hope you'll be there when we drift into it. Until then, rest well. Let your mind be full of stars. And remember, somewhere in the universe at this very moment, the light from your sun is passing through the void, traveling outward at 186,000 miles per second. A small, warm signal from a small, warm world, broadcasting quietly and without knowing it that something remarkable is here. Something that wonders, something that asks, something that for a little while tonight sat still and listened to the echo of the beginning. Sleep gently. Dream of the foam. Good night.